Hello everyone, we are Arturo Arjona
Alejandra Rodríguez.
and in this video we're going to talk about superconductors.
When an electric current is passed through a conductor, some of the energy is lost in the form of heat or light. The amount of energy lost varies depending on the individual material's electrical resistance. Some elements, like copper or gold, are great conductors of electricity and have very low resistance. Scientists discovered that the colder these materials are, the more conductive they become. But no matter how cold you make copper or gold, they will always show some electrical resistance. Mercury, however, is different. In 1911, the Dutch physicist Heike Kamerlingh-Ons and his team cooled a sample of mercury all the way down to 4.2 Kelvin, above absolute zero. Its resistance abruptly disappeared. This was the very first observation of the phenomenon of superconductivity. Superconductivity is a phenomenon of exactly zero electrical resistance and expulsion of magnetic fields, occurring in certain materials when cooled below a characteristic critical temperature. In a material, electrons collide with atoms and lose energy. As we keep decreasing the temperature of a material, we see that the free electrons stop colliding with the ions. So there is no energy dissipation. As a result, the resistance of the material also decreases to zero and starts behaving like a superconductor. The temperature below which a sample is superconducting in the absence of a magnetic field is called the critical temperature. When we place a superconductor in a magnetic field, we see that the magnetic field bends around the superconductor and it is not able to pass through it. So, the superconductor behaves like a perfect diamagnetic material. Now, if we keep increasing the intensity of the magnetic field, we see that a stage comes where the magnetic field penetrates through the superconductor and destroys the superconductivity. The magnitude of the magnetic field at which the superconductor loses its superconductivity is known as critical magnetic field for a superconductor. It is found experimentally and theoretically that this magnetic field is related to the temperature by the equation. In this graph we can see that the area under the curve is the superconducting phase, and the region outside represents the normal phase of the material. Suppose we have a superconductor and we pass an electric current through it. It behaves normal, but if we increase the current, we can see that above some specific current density, the superconductor loses its superconductivity and starts behaving like a normal material. The current density above which the superconductor loses its superconductivity is called the critical current density, and it depends upon, first, property of the superconductor, geometry of the superconductor, and the temperature and applied magnetic field.
One of the most characteristic properties of any superconductor is the Meissner effect, and it is the characteristic that any material that makes the transition from a normal to a superconducting state will actively exclude any internal magnetic field. As we have seen before, when a conductive material is exposed to an external magnetic field that changes over time, the conductor will generate internal currents that will create magnetic fields opposing the change in the external magnetic field according to Lenz's law. This is called diamagnetism. Knowing that the superconductors have no or almost no resistance to electrical currents, when applied an external magnetic field to a superconductor, the current produced will always be enough to counter the external magnetic field, having an internal magnetic field equal or almost equal to zero. Therefore, being a perfect diamagnetic or a super diamagnetic material. However, the Meissner effect is not equal to perfect diamagnetism. Knowing that a superconductor has no resistance to an electric current gives an explanation to its perfect diamagnetism. However, it is if the material was already applied to a steady magnetic field, then the transition from normal to superconductivity will result in a material that still has an internal steady magnetic field. However, this is not the case for superconductors. This sudden appearance of internal currents that result not from the variations of an external magnetic field, but from the transitions all superconductors go through is what is called the Meissner effect, and as well as perfect diamagnetism, the currents will counter any external magnetic field, resulting in an internal magnetic field of zero. The most known applications of superconductors is in quantum levitation, and it is possible by a process through which the Meissner effect is used in flux spinning. Although this is not the only method, in this practice a superconductor can be pinned with magnetic fields. Although flux spinning is not necessary for making a superconductor levitate in a magnetic field, it gives great control over the process, and it is highly necessary in temperatures that are near to 0 Kelvin. For this process, it is used more often than not type 2 superconductors. This is because the Meissner effect is not complete in these materials. The internal magnetic field is zero in most of its volume, except for some tubes called flux tubes, through which magnetic fields can flow. When a type 2 superconductor is applied to an external magnetic field, it will allow the magnetic field to flow only through these flux tubes, pinning the whole superconductor in place, making quantum levitation possible. Superconducting magnets are some of the most powerful electromagnets known, and therefore are used in MRI machines, mass spectrometers, in particle accelerators, and in tokamaks. They can also be used for magnetic separation, where weakly magnetic particles are extracted from a background of less or non-magnetic particles, as in the pigment industries. More recently, superconductors have been used to make digital circuits based on rapid single-flux quantum technology and RF and microwave filters for mobile phone base stations. Superconductors are used to build Josephson junctions, which are the building blocks of SQUIDs, superconducting quantum interference devices, the most sensitive magnetometers known. Promising future applications include high-performance smart grid, electric power transmission, transformers, power storage devices, electric motors, magnetic levitation devices, fault current limiters, enhancing spintronic devices with superconducting materials, and superconducting magnetic refrigeration. There have been presented many theories with the intention to explain their behavior. One of the most important is the BCS theory. Conventional physics does not adequately explain the superconducting state, and neither does the elementary quantum theory of the solid state, which treats the behavior of the electrons separately from that of the ions in the crystalline lattice. It was only in 1957 that three American researchers, John Bardeen, Leon Cooper, and John Schrieffer, established the microscopic theory of superconductivity. According to their BCS theory, electrons group into pairs through interactions with vibrations of the lattice, thus forming copper pairs, which move around inside the solid without friction. This solid can be seen as a lattice of positive ions immersed in a cloud of electrons. As an electron passes through this lattice, the ions move slightly, attracted by the electron's negative charge. This movement generates an electrically positive area, which in turn attracts another electron. The energy of the electrons' interactions is quite weak, and the pairs can be easily broken up by thermal energy. This is why superconductivity usually occurs at very low temperatures. However, the BCS theory offers no explanation for the existence of high-temperature superconductors around 80 Kelvin and above, for which other electron coupling mechanism must be invoked.